universal embezzlers, it's also about embezzlement of entanglement, like in the previous talk. So the beginning might feel a bit familiar, but then I will try to take a turn and tell you something different. So let's start this. I should say that our work here is based on some prior work that Rainer did with Volker Scholz many years ago, with some help by Ursula Hagerup, which is unpublished. Okay, so let's start. So maybe for those that are non-native English speakers like myself, let's look at what embezzlement actually means. So according to the Cambridge Dictionary, it's the crime of secretly taking money that is in your care or that belongs to an organization or business that you work for. And of course, here we're not really interested in money. We are idealistic scientists, but about resources in general. So you can try to embezzle all kinds of resources. Of course, many of you have seen this little animation of how to embezzle chocolate. Just showed once. So it's basically the same example as we had in the previous talk, the triangle. One problem with this example is that actually it's with chocolate, it's not a good example of embezzlement because you can detect very easily that something got embezzled. And you just put the remaining chocolate on a scale and you see it's lighter than previously. So really something's gone. So if you want to be successful as in embezzling resources, you better make sure that it's hard to detect. So it should be difficult to measure that we're embezzling something. So ideally, you probably want that your resource, the amount of the resource that you have in the beginning isn't even well defined. So maybe if you have a huge fluctuations in the initial resource, that would be the case. Okay, so now let's finally go to entanglement. So if we go to embezzlement of entanglement, then this would be, of course, the crime of secretly taking entanglement. And secret here is very important, as I would argue. And if you want to do this secretly, then you better make sure that no record of your crime exists. So in our typical example of LOCC, what this means is that Alice and Bob should not use classical communication because then eavesdropper could copy that information and publish it in the New York Times or something. So that's why I would say that if you want to do proper embezzlement, you better do it with local operations alone. And this is also what was considered first by Van Dam and Hayden. So what we have in mind ideally here is a scenario where we have Alice and Bob, and they somehow have access to some quantum system that's, each has access to one half of it, like the safe here. And this quantum system is characterized by some quantum state. Here, say for now on the tensor product Hilbert space of Alice and Bob. And ideally what they want to do is they want to apply local unitaries UA, UB to their local product state that they start with and obtain an entangled state. And they do not want to change the state on this resource on which they want to embezzle. Now, unfortunately, this is impossible. Okay? This is impossible because this would create entanglement for free. And this is also impossible if these Hilbert spaces are infinite dimensional. This is also impossible if these Hilbert spaces are non-separable, by the way. So it's shown in this paper. So it's just impossible. But as we have seen in the previous talk, I mean, this is a no-go theorem, so to say, but what you want to do when you have no-go theorems, you look at an approximate version and see whether now you can do something interesting. So as we see in the previous nice talk, Van Dam and Hayden discovered this nice family of states here, from which you can approximately embezzle in this sense. So if the rank, so if n here is large enough, the Schmidt rank of the state, then you can approximately embezzle a Schmidt rank D state up to this error, which you can make arbitrarily small as n diverges. So this is an embezzling family of states. This error here is essentially optimal. This was already shown by Van Dam and Hayden. And as we've just seen in the previous talk, whenever you have such a universal embezzling family, the Schmidt spectrum basically has to fulfill this 1 over J scaling. One very unfortunate thing about the scaling is that you cannot take the limit. Okay, so this normalization factor, which is the sum of basically sum over the 1 over J, does not converge, so you cannot sum it, so you cannot take a naive limit of the state, and therefore you see that you don't get perfect embezzlement. Okay. So today I want to sort of go beyond this framework of embezzling families, and I want to ask 3 questions. So the first question is there a quantum state that can embezzle states of arbitrary Schmidt rank to arbitrary precision? So a single state, not a family of states, okay? From which you can embezzle any state with any precision, even if there's arbitrary Schmidt rank. I would call such a state an embezzling state. Second, are there systems where all states are embezzling? Meaning that whatever state you have on that system, you can embezzle from it any other state. I would call such a system a universal embezzler. And then third, okay, suppose these exist mathematically, do they exist in nature? And I want to argue in this talk that all these questions have a yes answer. And I want to explain to you why this is the case. And the crucial step that we have to take in getting a positive answer here is that we have to go from a tensor product framework to commuting operator framework. So what does that mean? Well, usually we do quantum mechanics in this bipartite quantum mechanics in this tensor product framework. So we have Alice and Bob, each have their own local Hilbert space. And the joint space is the tensor product. The states are just, well, states on the Hilbert space. And the operators that Alice can control, so to say, are all operators on her Hilbert space. And Bob has all operators on his Hilbert space, well, bounded operators usually. And in the commuting operator framework, we elect some of these assumptions. So now we have one big joint Hilbert space, which is not a tensor product. Quantum states are just still quantum states. The operators of Alice are now some observable algebra in this big Hilbert space. Similarly for Bob. And of course, we have to assume that they commute, otherwise it wouldn't make sense. And we will impose 2 further important assumptions here that are automatically fulfilled in the usual tensor product framework. One is what we call hard duality, means that all operators that commute with Alice's operators are the ones that are controlled by Bob and vice versa. So the situation is sort of symmetric. And second, we assume for simplicity that there are no classical degrees of freedom, which technically means that the local algebras are factors. So that means that all operators within the algebra that commute with all the other operators are proportional to the identity. And all these algebras here are von Neumann algebras, meaning that they are closed in the weak operator topology. It will not be important to understand what really von Neumann algebra is for the rest of the talk. We will not go into technical details, but I will mention it. It is important that there are von Neumann algebras, though, and in particular that they are factors, because factors have a nice classification. So if you have a factor, you can classify it into different types. This is a famous result in mathematics. So first, you can characterize them into 3 different types called 1, 2, and 3. It's very simple. And then each of these types has subtypes. So for example, type 1 has infinitely many subtypes indexed by a natural number. And these algebras are simply the bound operator of a Hilbert space of dimension n. And n could be infinite, of course. Then type 2 has 2 subtypes, type 1 and type infinity. I will not talk about these in this talk, so we'll just go over them. And then finally, type 3 has infinity, a continuum of subtypes, labeled by a parameter lambda between 0 and 1. And the first 2 are often called semi-finite. They have a trace function. And the type 3 ones are called purely infinite. They don't have a trace. That's because if you look at the projection operators in this algebra, then they always project on an infinite dimension. Infinite dimensional subspace. Okay, so I just tell you this. You will see it later. You don't have to understand where this comes from. So usually when we do entanglement theory for pure states, what we want to do, as we saw in the previous talk as well, is to go from the bipartite setting where we have pure states on the tensor product Hilbert space to a local setting where we only care about reduced states, and we do that using Nielsen's theorem. So we go from pure states on a Hilbert space basically to majorization theory and reduced states. And we want to do the same for embezzlement. So the first result that we derived was that whenever you have a situation where you map with local unitaries this omega state, tensor product state, to some entangled state with a small error, then this equivalent to saying that you do the transition on the marginals only. Okay, so little omega A is the marginal of big omega, psi is the marginal of psi, and these two are completely equivalent. So we can reduce, just as in the usual entanglement theory, we can reduce everything to just the local setting, which is nice because we don't have to think about the two parts. So to make progress, we introduced this quantifier for embezzlement. So this quantity kappa here is supposed to measure the quality of the state to act as an embezzler. So what we do here is we do a worst case sort of bound, or worst case error. We first optimize over all finite dimensional quantum systems, all dimensions. Then you optimize over all states rho sigma with this dimension, and you ask whether you can map omega tensor rho to omega tensor sigma with the unitary. And then, of course, you take the infimum over all unitaries. So if this is 0, then this state is an embezzler. It can do a state transition from any rho to any sigma of any dimension, to any error of the one. And this quantity will play a central role in it. Indeed, once we have this, okay, actually before that, once we have this quantification here, we can also look at the best worst case error. So to say, we take the infimum over all states on our algebra, or we take the worst case error, which we take the supremum over all the states in this algebra. And these are these two quantities, kappa min and kappa max, are what I will care about in the rest of the talk. Indeed, with this, we can already state our main result, namely that we have this little table, which is the types of von Neumann algebras of vectors up here. And then we have the subtypes, and now we have kappa min and kappa max. So let us go through this table. So in these types 1 and 2, we have kappa min equal to 2, kappa max equal to 2. Both are the maximum values that kappa can possibly take. So there are no embezzling states of these algebras. For type 3, however, let's first look at lambda between 0 and 1. We see that kappa min is 0. So there are some embezzling states. And in fact, if you take lambda equal to 1, all states. So we see here that in the case that you have a type 3, 1 von Neumann algebra, you find that all states are embezzling. Just to reiterate this, if you would have a quantum system that's described by such a von Neumann algebra, then every single state on the system would be an embezzling state. So from every such single state, you can embezzle any state of any Schmidt rank to any precision. Okay. Good. And we see that in type 3-1, we have all states are embezzlers. In type 3, lambda with lambda between 0 and 1, we have always one embezzler at least. And kappa max is this funny function depending on lambda. And type 3-0, well, this is a case for its own very complicated case. I will not talk about it in this talk. One nice thing about this is that if we really only look at type 3, you see that you can actually read off lambda from kappa max. So you can invert kappa max as a function of lambda, which means that this kappa max, which is an operational measure for embezzlement, reveals the classification of type 3 lambda factors, which was originally given by Kohn in famous result. So that's very nice. So it gives a sort of operational way to classify von Neumann algebras. So this is the math side. The question is, of course, whether this has any interesting physical implications. But before we get there, I want to tell you a bit about the fundamental ingredient that we use to derive these results. So the fundamental ingredient is a mathematical technique called the flow of weights. And I would just treat it as a black box here. What the flow of weight does, it takes a von Neumann algebra and a state on this von Neumann algebra, and it spits out a classical dynamical system and a probability distribution on this classical dynamical system. So the system depends on the algebra, and the state you get out depends on the state. So we have two types of mathematical objects here, von Neumann algebras and classical dynamical systems. And on the von Neumann algebra side, we're interested in the embezzling states, and standard quantity or standard objects you want to look at if you have a dynamical classical system is you want to look at invariant probability measures, like stationary states. And it turns out that there's a very nice connection between embezzling states and invariant probability measures, namely they are precisely the same. So an embezzling state is mapped to invariant probability measure, and if you have an invariant probability measure, there's an embezzling state. In fact, even more is true. If you look at this quantifier of embezzlement, it exactly is the measure for how far the distribution here deviates from being invariant under the flow of the conservative dynamics that we have, flow of the classical dynamics. And if our von Neumann algebra is a factor, then it turns out that this flow is ergodic. So there's at most one such invariant probability. Okay, so this is sort of the fundamental theorem that we have to prove. I will not tell you how we can prove that. It would be way too far. So for us, this is just the black box here. But what I do want to tell you is what are these classical dynamical systems for the type 3 lambda, type 3 lambda factors? Because they're very simple. If you have a type 3 lambda factor, what you have is you have a circle, and basically the radius depends on lambda. It becomes bigger as lambda approaches 0. It becomes smaller as lambda approaches 1. And the dynamics was the rotation of the circle. And then it's obvious that you have an invariant probability measure because, well, you have the uniform distribution on the circle. And as lambda actually takes the value 1, this whole thing contracts to a single point. Meaning that the classical dynamical system is trivial. It consists of a single point. In particular, every state on a single point is invariant because the dynamics is trivial, and therefore every state is invariant. So this is the gist of the idea. So why are type 3-1 factors universal embezzlers? I want to tell you a bit more about this. So type 3-1 factors have two crucial properties. First, by result of Kohn and Störmer from 1978, the factor is type 3-1 if and only if any two states are unitarily equivalent, in the sense that you can map any state to any other state in arbitrary precision by unitary rotation. This is completely different from our usual quantum mechanics that we are used to, because there we have the spectrum as an invariant. Here we don't have a spectrum, basically, and therefore that's possible.
Oh, no. Okay.
And the second property is that these type 3 factors are properly infinite, meaning that if you take the algebra, it's actually isomorphic to the algebra itself, tensor the bound operators on any Hilbert space, separate with Hilbert. So the second property tells us that we can actually compare states on the algebra with states on the algebra tensor some Hilbert space, basically. So the type 1 factor here. And the first property tells us that if we do this, we can map the state on M to the state on the tensor product by unitary. And therefore we have embezzlement.
Oh. Otherwise, it's going to switch.
Okay.
Okay. I'm not going to touch it for that.
So where do we find these type 3-1 algebras, type 3-1 factors? So far it was all math, and the rest of the talk I want to tell you basically that there's physics to it as well. So there are basically two arenas of physics where you can find these. One is statistical mechanics when you consider infinite spin chains, and the other is relativistic quantum field theory. So when I first talked about statistical mechanics and infinite spin chains, to give you some more intuition about this phenomenon of universal embezzlement. And then I will talk a bit about quantum field theory. So I just told you that type 3.1 are universal embezzlers, but why is it the case that the only universal embezzlers are type 3.1? This is what I want to explain to you using the example of infinite spin chains. So it's a very known result that all separable infinite dimensional Hilbert spaces are isomorphic. So if you have any such Hilbert space, you can always think of it, if you want to, as the Hilbert space of an infinite spin chain relative to some reference product state. So here's such an infinite spin chain with a fixed product state on it. And if you have such a system, then the states on it are basically given by states that deviate on any arbitrary number of finite number of spins arbitrarily from the reference state, but that asymptotically converge to this reference state. In particular, you can, for any error that you wish, you can define an n so that you can approximate the state by just a tensor product on the first n spins with the rest, and where you put the rest in the reference state that you started. And so this is how you describe different spin chains. Okay. Now suppose that this infinite spin chain is a universal embezzler, meaning that any state is an embezzled state. Then, since this is infinite, it turns out that the spin chain, if you only start in the n spins, is still isomorphic to the original spin chain. And that means that this state, when you only look at the spins with number larger than n, must be embezzling itself, because we assume that the whole thing is universal. So let's now take two states on the system, and we approximate them by a tensor product with a reference state for some sufficiently large n, so that these errors are as small as we wish. And now we find that this state is an embezzler. Therefore, we can map this one to this one. But now if we go the circle here, this half circle, then we can actually close the circle and say, okay, actually this means that we can map omega to sigma, which means that all states are approximately unitarily equivalent. And by the result of Kohn and Sturmer that I just showed you, this means that the algebra must be type 3.1. And it's important to mention here maybe that actually you can find any type 3 type in these infinite spin chains. So these actually provide all the examples in a certain sense. Okay. One other nice thing is that suppose we have an embezzling state on this infinite spin chain, then we can show that if you only look at the first n spins, you actually get an embezzling family in the sense of what we discussed in the beginning. I will later say this a bit more about the conventional embezzling family, but not much. Okay. So this is so much for statistical mechanics examples. And now let's go to quantum field theory. So for the purpose of this talk, what a relativistic quantum field theory does is the following. Here we have a Penrose diagram of Minkowski space. And what this field theory does for us, it maps to any open subset of Minkowski space in von Neumann algebra. Take the von Neumann algebra of the operators supported in that region of space-time. And this has some properties, this mapping. Well, first, of course, if the two regions are space-like separated, then the operator algebras should commute. Second property is that they should be causally complete, these algebras, meaning that, so if we start with this circle O here, then we can take what's called the causal complement, which is this red region here, with all the points that are in the causal complement. And then we can take the double causal complement of which is the causal complement of this, which is this light blue shade here. And the causal completeness says that the algebra generated by O is the same as the one by O double prime. And then the third condition is the Haack duality condition, and this actually where we take the name from the general example, is that the algebra of O prime is the commutant of the algebra of O. And so basically taking commutants in the operator algebras is compatible with taking causal complements in space-time. So this is the basic structure that we will use here. And now from what I've told you before, then basically you should have taken that when we want to say something about embezzlement, what we have to check is the type of the von Neumann algebras that we get. Now, luckily, we don't have to do this because algebraic quantum field theorists have been interested in this question for a long time already. So if we have a situation like this, where say Alice has this left half, this left wedge of Minkowski space-time, Bob has this right wedge, then it has been shown under extremely general assumptions that the algebras are type 3-1. What this means is that in such a situation where we assume, okay, it's not a very realistic assumption, admittedly, that Alice controls one half of space and Bob the other half, we find that relativistic quantum fields are universal embezzlers. So we have, say, the vacuum state of your relativistic quantum field, you can embezzle any state that you want. This is nice because it gives a sort of operational interpretation of the diverging vacuum entanglement. So you probably have heard at some point that you take a relativistic quantum field, the entanglement between the region and its complement is unbounded, it's infinite entanglement, so to say. And the technical way to express this is that the algebras are type 3-1, and now we have an operational interpretation of this, maybe using embezzlement. The second nice thing is that in 1985, Stephen Summers and Reinhard Werner showed that from a relativistic quantum field, you can violate Bell inequalities maximally without actually setting up a source. You just do measurements. And now our embezzlement result explains very clearly why this is the case. Because if you have such a situation, what Alice and Bob can simply do is they can embezzle a Bell state and then just do any old Bell measurement experiment. And therefore violate Bell inequalities as much as they wish. Okay. So to summarize, what I try to convince you of is that it makes sense to speak of embezzling states that are quantum states that can embezzle any finite dimensional entangled Q state to any precision. And that even they are universal embezzlers, meaning where every state is an embezzling state. And that potentially even these things exist in nature, at least if our assumptions about quantum field theory are true. So these should all get a check mark. So what are some open problems with this? First, in this QFD setting, it will be interesting to know whether Alice and Bob can localize the operation close to the space-time region where they meet. So right now, I told you that they basically have to control all of space-time. That seems a bit unrealistic. But there's good reason to believe that they can actually localize the operation close to the area where they sort of meet. Second, it would be nice to maybe explicitly determine the embezzling unitaries maybe in a free quantum field theory and see whether like how the trade-off with energy investment, for example, would be how difficult it is to sort of actually realize such unitaries. And third, there's an open problem regarding embezzling families. So I told you that if we have an embezzler, then we can, in this infinite spin change, we can restrict the first n spins, and this gives us an embezzling family. Conversely, it would be interesting to see whether one can get embezzlers as limits of embezzling families, in particular of the Van Damme-Hayden embezzling family. So there's a way to take a limit of that family. However, what we get there is we get the so-called tracial state on the type 2-1 factor. I told you before that type 2 is not embezzling. It's not doesn't have embezzling state. So this has the funny consequence that you can sort of take a limit of the Van Damme-Hayden family where the limit is not embezzling. But we don't know whether there could be other ways to take the limit, which actually gives an embezzler. And with that, I would like to close and thank you for your attention.
Thanks. So we have taken the liberty to add some time to the program, so we have time for questions.
Okay, could you explain why is there a discontinuity for lambda equal to 0 of kappa min? I mean,
Why the
here, show the table on the previous slide. So at lambda 0, you have 0 point something to AC correct or 0 comma.
Well, this suppose there's a question mark. So type 3 0 is famously difficult to deal with.
Okay,
The
but
reason that-
for any lambda equal to epsilon, that's fine, huh?
Sorry?
For any small lambda, that's fine, larger.
Yeah,
than
yeah, any finite lambda
Okay.
between 0 and 1 is fine. So lambda equal to 0, these algebras really cannot be classified in a certain sense because to any, okay, technical statements, to any what's called a properly ergodic classical system, there exists one type 3-0 algebra. So you would have to classify all properly ergodic classical systems, which somehow is impossible. So here we have a question mark. So we know that there are type 3 zeros factors where you have embezzling states. We also know that there are type 3 zero factors where we certainly do not have embezzling states. We cannot prove at the moment that this should be any certain number. We know that here the question mark has to be a number. So for any t between 0 and 1, you can find algebra where kappa min is certainly larger than this t. But we don't know whether it actually might just be true in these examples. So this is a big open problem, but it's very technical.
Let's go ahead and project a bit. So I'm just wondering in this like semicircle proof of the infinite spin chains, this epsilon unitary equivalence, whether the argument is somehow sort of I mean, I could completely be misunderstanding this, but is it kind of like a definite argument on the marginals that they're kind of close when you take this reference state, or?
No, it's really more about the definition of how you even deal with infinite spin chains. So you cannot naively take an infinite tensor product. So to define that properly, what you basically have to take is finite deviation from the product state on finitely many spins, and then comes out that the sort of the state space is just states that have this approximation property. Okay, and then to make the circle is use embezzling.
I have a question about your how you evaluate your omega function. So your omega kappa function, kappa function. So you have a supremum over all the reference dimension.
Yes, that's right.
So how do you? So is this quantity will stop at certain n? So certain n. For example, there's a threshold n 0.
No,
No.
because if that would happen, then it wouldn't be true that in the type 1 case would get true because we know that the Van der Heyden examples, right? So you would only have to consider the finite dimension of state that you want to embezzle. You wouldn't get true here because we have the example of Van der Heyden, which gives you something smaller.
So this means that it will increase over,
Yeah.
and it will strictly increase.
Yeah.
It will next. Okay, thanks.
I think we can have the next speaker set up and one last question.
Hey, I had a question, and that is that if I want to create and use an embezzling state, usually that's associated with infinite physical resources, or there's some that I need to put some cutoff at some point if I want to consider creating that embezzling state in some physical setting. Could be an energy cutoff in a quantum field theory, could be a number of subsystems in a if I have a spin, qubits that I want to entangle. My question is, in your general characterization of these embezzling states, can you see this physical parameter? Is there a natural parameter that acts as the physical resource that you might want to cut off if you wanted to consider these states in a more practical setting?
Not in the abstract setting. No, I couldn't think of such a problem.
I don't know.
One thing I should mention maybe is you might have seen in the end, like the one check mark has an asterisk.
How about can you just share your screen?
So there's a little asterisk here. And the reason is the following. So I told you that the local algebras in relative secure here are type 3-1. There have been papers released by Edward Wilming, Jeff Henrik, and before others, where they argue that once you incorporate gravity, it might be the case that your algebra is actually type 2. So in that case, gravity would sort of disable embezzlement, is true, and would maybe provide the cutoff that you're looking for. But of course, I mean, I don't know anything about quantum gravity, so it's as much as I can say about it.